So if you, for instance, colored the top half yellow and the bottom half blue, like now we can ask the same question, what motion in a space will leave it invariant? Like so that, somebody wouldn't be able to tell that we have moved. And now we notice that, for instance, if we do like a reflection top to bottom, right? Like you can tell that I moved it because the blue went to the top and the yellow went to the bottom.
Of course,
So now the only possible choice seems to be that we can reflect it from left to right.
And this connection of numbers and symmetries is a real one, right?
Exactly, because in mathematics, one thing that we love to do is abstract from what we know. Here we have the numbers, and this forms a set.
They're just a collection of entities,
a collection
of things.
You see, you're combining two things that are the same in the same set, and making a new one.
Yep.
Right? If you take an integer, like let's take -4, and you add it to 2, we get -2, which is again in the set.
Right.
And if you add 2 plus 4, you get 6.
Right, so always getting some other thing on the line
in
there.
the lines.
Yep. Right.
So this is an example of a binary operation. Binary meaning 2. You take 2 objects, you combine them, and you get a new object that is back in the set.
Right.
And this we call closure. Like the operation doesn't take you away from the set.
Okay, so we have our binary operation, and it makes sense for this collection of integers in the sense that if I take 2 of them and do addition, I get another one.
Exactly. Right? So now you might ask, what other properties does this operation have? So let's say I give you 1, 2, and 3. And I ask you, add them, give me the results. If somebody's new to it, we'll go 1 plus 2, and then add the third number to the result of 1 plus 2, or go 2 plus 3 and add that result to the
to 1.
Right? So, and the question is, do we get the same answer when we do it in these 2 ways?
Yep.
Right? And this is the property that we call associativity. So another thing that is quite an amazing thing is there an element such that when I combine it with any other element, it doesn't change the value.
Right.
Like, it's like, is there an identity element, something that doesn't change?
An identity element,
an identity element. If we add 0 to any other integer, we get whatever integer we obtain. So for instance, if you get 4 and you add it to 0, you
still have 4. So
and
4 retains its identity.
So and even if we do it in either way, 4 plus 0 or 0 plus 4, you still get 4. And this is the property of having an identity. So now that you have an identity element, you might ask yourself, if I give you an element in the set, is there an element that would give us 0? So for instance, if I give you 3, you might come up and say, you add -3 and you get 0.
Right. So every element on the line has its negative, and those are sort of specified by the fact that when you combine those two, you get this identity.
This identity element, and this is the existence of inverses.
Of inverse. In this case, an additive.
An additive inverse, exactly, for the integers. So these 4 axioms have been recognized as being special. You start with a set, you add closure, associativity, you have this identity element, and you have this inverse for every element in the set. And these 4 properties what forms a group. This is, is a set with these 4 properties.
And it's sort of amazing that out of those 4 axioms, somehow that you get an incredible richness, from the wallpaper groups that we saw to, groups in physics. We've been talking about groups in a very geometric way, moving designs around, moving shapes around. But in fact, the birth of group theory was much more formal, right? Sort of closer to the algebra that people think of being algebra. Isn't that right?
Usually what people think about when you say algebra, they think, high school. But the first person to use the term group was Évariste Galois.
Very famous mathematician, and we're going to hear his fascinating story right now. Let's take a look.
Let's take a look.
A firebrand radical Republican who lived in the time of King Louis Philippe, Galois was just 20 years old when he solved one of the most hotly contested problems in mathematics, the problem of solvability by radicals. And it goes like this. Under what conditions could you find a formula for the roots of any polynomial in terms of the coefficients, using only the usual algebraic operations and application of radicals, square roots, cube roots, and so on? Galois' quest was a powerful result, to be able to say for any polynomial with integer coefficients, both when it was possible and impossible to find one of these simple formulas for its roots in terms of the coefficients. Galois' epiphany was to consider the symmetries of the roots of the polynomial. The young Frenchman's answer became known as Galois theory and is the basis of modern group theory and our understanding of the mathematics of symmetry. On May 29, 1832, Galois is said to have worked through the night desperately composing his mathematical treatise summarizing 6 years of work. It was the night before he would be fatally wounded in a duel. With apparent foreboding, Galois wrote, "I have no time." While the circumstances remain murky, the duel may have been the result of romantic entanglement or political intrigue. Galois' legacy is the algebraic basis of our understanding of symmetry. So Galois discovered a set of conditions in terms of the symmetries of the roots of the polynomial that could determine if the polynomial could be solved by radicals. But the roots are numbers, and what could it mean to consider the symmetries of a collection of numbers? Well, let's take a step back, all the way back to the simple example of the quadratic formula. Really, the quadratic formula tells us two things. The familiar one is that from just the coefficients of the polynomial, I can write down the roots. But it also works in the other direction. Knowing the roots, I can figure out the coefficients of a polynomial that they turn into 0. So Galois' idea was exactly to adapt this backward point of view and add a very clever twist. He would use these roots as the basic ingredients to start making numbers. He'd take the roots, toss in all the rational numbers too, and then see what numbers he could make by taking arbitrary sums and products. Like taking a pile of atoms and seeing what sorts of molecules you can make. Decades later, scientists would begin to understand the properties of molecules by determining their invariance under symmetries that mix up the atoms. In a similar way, Galois discovered that the ability to solve a polynomial built out of some roots depended on the invariance of those numbers created from the roots after permuting the roots. Permuting. It means mixing up or shuffling. And in order to see what we have is a group, let's actually think about shuffling, but card shuffling. Here's a familiar old deck of cards, and notice that any shuffle or rearrangement of the deck leaves it invariant. In our new language, it's a symmetry of the deck of cards. Notice that if I do 2 shuffles in a row, I get another shuffle, so closure. Notice that for every shuffle, there's an inverse shuffle. Just the one that undoes the shuffle. Not doing anything at all gives me the identity shuffle, and take my word, associativity works. So the shuffles of a deck of cards are a group, and it turns out that the structure of the particular shuffles that Galois considered on his roots are what give the conditions for solvability by radicals. Using shuffles to understand polynomials is a pretty good trick. But an even better one is using the algebra of shuffles to actually understand card shuffling, which is something that people have been doing for decades, culminating in the recent mathematical discovery that in order to mix a deck of cards by riffle shuffling, that is, it takes 7 riffle shuffles to randomize an ordered deck of cards. This was proved in 1992 by Percy Diaconis and David Beyer. Diaconis and Beyer identified a key signature of a shuffled deck of cards, the number of rising sequences. Let's look at an example. I start here with an ordered deck of 10 cards. Riffle shuffle them once and take a look. See how it's now composed of 2 rising sequences, 2 subsequences of increasing cards. And as I continue to shuffle, the order dissolves. After I do another shuffle, I expect 4 rising sequences. And then after that, 8, and so on and so forth. The way in which permutations of a given number of rising sequences compose their algebra provides the key to understanding how the mathematical model of riffle shuffling works. This is just one example of what is in fact a very intriguing intersection of the world of cards and even card tricks with mathematics. But here's another trick. Did you know that we can use symmetry to uncover the virtually invisible worlds of the atoms in a crystal? Well, we can. Let's take a look.
So crystallography is the study of how atoms or molecules are arranged in the solid form. My name is Mary McGrath. I'm the Senior Director of Structural Chemistry here at Gilead Sciences. Our goal at Gilead is to get safe and effective drugs to patients sooner. So in the field of crystallography, symmetry is very important. Symmetry tells you how each molecule in the crystal is related to the other molecules. So we need to know that information in order to get out our final picture of what our protein looks like. It's also very important in just trying to complete our experiments successfully. We need to know those relationships. What we end up doing is using math as a lens to refocus our image. When we are able to provide a picture in crystallography of the protein target to the chemists, they are able to specifically design for that protein. So what ends up happening is you accelerate the drug discovery process. Instead of taking 10 years to come up with a potent compound, maybe now it would take 3 or 4 years. Our process has many parts to it, and one of the things I really love about being a protein crystallographer and doing structure-guided drug design is that we use techniques that have really not changed all that much for, close to 100 years, and we use other technology that's just changing all the time. So it's a really fun blend of the traditional and the cutting edge.
The uncovering of symmetries in a crystal are just one example of the use of symmetry in physics. A much more mysterious fact is that laws of nature generally exhibit some sort of invariance. A fact proved by Emmy Noether, perhaps the greatest woman mathematician of the 20th century. A prime example is the law of conservation of momentum that comes from the spatial invariance of the laws of motion. Fundamentally, the world works via symmetry. The symmetries of nature, the patterns of the Alhambra tilings, the manipulations of mathematical equations, or a deck of cards. Whether we're talking about symmetry as a property or as a transformation, it creates the emotional responses we feel in the presence of beauty, whether it's art, math, or butterflies.